Okay, so we're going to be analyzing the gain of a common emitter amplifier. So first of all, let's look at the terminology of common emitter. So with an amplifier, we're basically going to be applying my input right here. Now in this case, we're not really going to be worrying about the biasing, but the transistor has to be biased, but that will be covered elsewhere. So basically you see that the input is connected in through the base, the output is connected to the collector. So the terminal that doesn't have an input or output is the emitter. So that's why it's called a common emitter, because that's the one that doesn't have an input or an output connected. We're trying to calculate the gain, which is defined as V out over V in. So in order to solve that circuit, we're going to have to replace the BJT with our small signal model. So we're going to start with the small signal model. So it has an R pi, and the voltage across it is V pi. We have a dependent current source, which is GM V pi, and it has an RO in parallel with it. This is my collector, this is my emitter, and this is my base. So now I'm going to come in here, and now we have this transistor is right here, and we're going to come in here. Here is the emitter with the E. I'm going to put a ground right there. Okay, here is my base, and so this is going to be equal to my V in. And then over on the collector, I have this voltage, this resistor going up to a 10 volt. Well, when we're doing gain, we're only looking at AC gain, so we're using superposition, and we're only doing the AC part, so this DC part becomes a ground. So we have RC, and then this point is ground. Well, if most of my grounds I draw on the bottom of my circuit, but this ground's up at the top. So I'm going to take this resistor and flip it down to ground. So I'm going to go draw it like this. Even though in this circuit it looks like it's going up, but up and down are the same thing if this part becomes ground. So this is my circuit right here. So now I just need to solve this circuit. So what we're going to do first is solve for my V pi. Well, since this point, you see we can come in here and simplify this and draw this as ground and this as ground. So we see that these two are in parallel, and my V pi is just a voltage divider. So we have V pi is equal to R pi, whoops, this isn't even a voltage divider. This is just straight across there. So V pi equals V in, and then all of this current goes through that parallel combination. So we see that V out is equal to minus RO in parallel with RC times GM times V pi. Well, V pi is equal to V in, and we take the V in off and move it over here. And then I have this is my gain equation here. Okay, so we have a cheat sheet, which is over there for my different configurations. So here is my configuration that I did right now. Here's my RC, VCC, V out. So this is my common emitter, and you see this is my equation right here, and this equation right here is the same as that equation right there. So this is the gain equation for a common emitter amplifier. Now the other things that we want to do, if I go back to my sheet, we see that we also want to calculate, well, what is the Thevenin equivalent resistance for my input, and what is the Thevenin equivalent resistance for my output? So what we see here is these things are just independent of the configuration. and they're just looking into certain terminals of the transistor. So let's look at this. So we have this. So this was ground, and we're looking in here. So this is my R in. So I'm just going to draw my small signal model. GMV pi. This is my V pi and my R pi. My emitter is ground. I have something connected up here. So we're going to put a dot, dot, dot. And I'm looking in here for my R in. So what we're going to do is we have a dependent source. So we're going to put in a test source, V test. We see that this point is just ground. This point is just ground. So what we see here is that there's no real connection across there. So there's no current across there. So we see my only element is the R pi. So R in equals R pi, which is, this is right here. Okay, so this is an AC ground. That's what the little AC means. If I'm looking into the base of the transistor, even if I put something up here, my value is R pi. Okay, so now we want to look at our output. So we're going to be doing this one now. So now we're coming over here. And we can have anything we want connected over there. And we are looking in this point, which we're going to call R out. So again, I go to my small signal model. I ground my emitter. I can have something connected over here if I want to. And then, oops, this is GMV pi RO, and then I'm looking in this direction. So I have a dependent current source, so I'm going to put in my test voltage. And over here, you can see over on this part here, I could have other resistors, but there's no voltage sources, because if there was an independent voltage source, those get turned on. So let's just say it's some resistor over here. Well, if I just have a resistor over here, because of KCL, there's no current coming in here, because there's only one wire that crosses, which therefore means that this voltage right here is 0 volts. If that's 0 volts and that's my V pi, then this is gone because it's just 0. And then if I redraw my circuit, I get this. So we see that R out is just equal to RO. Going back to my little test sheet here, that's this part right here, which is the RO. But in our actual circuit right here, we have an impedance looking down, and we also have an impedance looking up. So our actual R out is going to be equal to the RO, which is the part looking down, in parallel with my RC. So in our actual common emitter amplifier, we have to take into account the RC looking up. Over here, we don't have to worry about it. So now to review our common emitter, here is our gain equation right here, minus GM times RO in parallel with RC. It has an input impedance of R pi and an output impedance